All right, folks, Mr. Bucko here with your target from 11.5 from geometry, which is to be able to find the distance between 2 points, which is something we've done before. We're just going to apply the distance formula to find the distance between 2 points. So what does that look like? Looks like this. The theorem, or the Pythagorean distance formula on the coordinate plane for the distance between 2 points. And it says Pythagorean here because this is basically the Pythagorean theorem. That's all that it is. The only difference here is that we're not dealing with a triangle with given side lengths. We're given coordinates on a plane, and then we're finding the distance between those 2 points. But those 2 points can form a right triangle, which is where the Pythagorean theorem comes into play here. So the distance between, which we're going to call D, the distance D between 2 points, and we're going to have point 1, x1, y1, that's some point on the coordinate plane, and x2, y2, that's another point on the coordinate plane. The distance is the square root of the entire quantity of the difference of the x values. So you take the difference of these two, which gives us essentially that one side of a triangle, squared, plus the difference of the y values squared, which is kind of like that a squared plus b squared, and this will equal c squared, but this isn't squared because we're taking the square root of the whole thing. So it's exactly the Pythagorean theorem, just in a different format because we're using coordinates instead of actual measured distances of a triangle. So what does that look like? Here's an example. We're going to find the distance between 12, 23, and 17, negative 8, and we're going to do that to the nearest tenth after we evaluate the square root of whatever it is we need to find here. So we have our values. We have our x1 and y1 and our x2 and y2. And you'll notice that I called 17 x1, and therefore negative 8 is y1, and therefore 12 is x2, and 23 is y2. I could easily switch these around. If I wanted to call 12 x1, then I'd have to call 23 y1, and then I could call 17 x2 and negative 8 y2. So these can be swapped around, but we always want to make sure that whatever we call x1, it goes with y1 in that same ordered pair. So we have these, and now all we're going to do is just plug them into the distance formula. There's our distance formula right there, and we're just going to plug in the values that we've assigned right here to the formula. So x2 is 12, so we have 12 minus 17, because 17 is x1 squared, plus 23 minus negative 8. So one thing to note here with the distance formula that might be an oversight when you're doing the work or just in general is that the minus sign in the formula is not the same as the minus sign or the negative sign of the coordinates. So these two things right here in particular are not the same sign. So that's why they're doubled up here. So 23 minus negative 8. You don't just say, well, there's one on each of them, so I can just eliminate one of them. That's not the case. So 23 minus negative 8, and then we're going to square that. So if we simplify this, we get negative 5. Negative 5 comes from 12 minus 17. 12 minus 17 is negative 5. And notice I still have that in the parentheses because that entire negative 5 will be squared. 23 minus negative 8 is like 23 plus 8. 23 plus 8 is 31. So we're going to have 31 squared. So now we do our exponents here. Negative 5 squared is positive 25, and then 31 squared is 961. Add those two together, and we get 986. And the square root of 986 will be the distance between these 2 points. What's the square root of 986? I don't know. Plug that into a calculator, and you get approximately 13.4, and that's rounded to the nearest tenth as we were instructed to do. So that's how you find the distance between 2 points.